All right, so let's get started. Just going to share my screen. And Dr. Danish, I've made you the co-host so you can let people in as they come into the waiting room. And I would, perfect. And I would also request everyone else that I'm a bit bad at checking the chat every now and then. So if you can speak up, if you have any comment or question, just unmute yourself and make a comment or ask your question, because I check chat at regular intervals once I'm done speaking. So if I miss out your question or comment, just unmute yourself and let me know. Okay. All right. And if anyone of you notices a comment in the chat or question in the chat which I haven't answered, just unmute yourself and let me know, because I might miss it. And I speak. The common complaint I get in my classes is that I speak very fast. So if I start talking very fast, or if I start going at a faster pace, just slow me down and ask your questions. Okay. So I'm just going to share my screen now, and let me know if it's visible to everyone. Just somebody unmute yourself and let me know.
I can see it.
Yeah, it's visible. I can see your screen.
It's visible, sir.
Perfect. Perfect. Thank you. Okay, so this is going to be a different theme this week, and I decided let's take a little bit of time to, before we get into the language of mathematics, right? So we named this week as the mathematical language. That was the name that we've given this week. But before, and we'll get into what I mean by mathematical language. It's not a concrete idea as much as we'd like it to be. But before we get into that, I want to have a conversation which might go slightly towards a philosophical perspective, but I want to have that conversation. And I mean, mathematics does have its roots in philosophy. So, I mean, in earlier times, mathematicians and philosophers were kind of the same people, but the specialization sort of came into picture when mathematics started getting more and more developed and more complex. So we had that divergence between these two things. But initially, philosophers and mathematicians and thinkers, they were all the same people, because they were all sort of trying to answer the same kind of problems. So let me put out a question to everyone in the audience. And the question is as follows, and I would like to know your perspective on this, which is a very basic question. It says, basic as it gets, what is mathematics? And specifically, what is mathematics to you? I think this last bit is important, because right now you've been exposed to perhaps a limited amount, let's say, of mathematics. So I want to know, what is mathematics to you? And I'm not looking for a textbook definition, right? I'm not looking for a specific set of words. I just want to know your perspective. So anyone? And please, again, if you're writing in the chat, I would prefer that you just unmute yourself and just converse with me.
Math is a formal science built upon a few axioms, not a few, quite a lot of axioms, and it's built upon logical deduction. using some logical principles like logical transitivity.
Mhm. So it's built upon logical axioms.
Principles like truths.
Okay, principles and proofs. All right, principles and proofs. Okay, there's a lot to unpack in that answer. But before I get into specifics of what you just said, I would like to have a few more answers if people are willing to share.
May I go ahead?
Yeah.
I'd like to add that mathematics to me is a way of quantifying the world
Okay.
in terms of data and how we analyze all that data.
Okay. Quantifying the world, data, analyze that data. Okay. Anything else you want to add to that answer?
No, I think that's what I'm going to keep it to.
All right. So this was Ahmed, right?
Yes, sir.
Okay. Thank you, Ahmed. Anyone else would like to share their perspective?
Sir, I think that maths, in my opinion, is an attempt at explaining everything in terms of a language that we can universally all can accept, that is logical and reasonable to us, even though
Okay.
it may be it's a system that it is incomplete, it may have its flaws, but as humans, it still has flaws. So that's maths to me.
Okay. Anyone else? These are great answers, by the way. Lot of things to unpack in each of these answers. Anyone else has a different perspective on mathematics to them?
Math also studies some objects like graphs, groups, rings, numbers, graphs. Yes.
Okay. So is this a rhyme, right?
Yes.
And you also gave the first answer?
Yes.
Okay, so I'll just add this to your first answer, which is it's a study of objects. And what kind of objects did you mention?
Abstract.
Abstract objects. Okay. All right, great. Anyone else? Yes, Hossamuddin, go for it.
Sir, for me, if you ask me what's math, so it's basically everything and anything in life. So like if you say for say like if it's a graph, if it's some chance, like if the chance of the next day being a rainy day, that's also related to life. But in the end it's math. So what I believe is everything and anything in life is math. And the application of math is not just like logical and calculations, it's way beyond that. So that's my take on what's math for me.
So when you say, so I'll just add it here, beyond calculations and logic, could you be more specific about what you mean when you say it's beyond calculations? Like, could you give me an example, perhaps?
Sir, like let's say calculations like for example, like any calculation math, let's take an example of calculus. So like if we are applying calculus, okay, so like there are two perspectives. So there are people who do math just for the sake of doing math, like you know, like the solving questions and all, but there are people who do math not for the sake of doing questions, but for the sake of applying the knowledge, relating things to what they see around them, the things they see around them, and that's what math really is. Basically, when you add math with philosophical thinkings and all, that what math really was, is, and should be.
Okay, what it should be. So you think that the people in the second camp who are applying mathematical language, they're the ones doing the real job, because you use the word of what it should be.
Yeah, I guess that's the real essence of math, because like just for the sake of calculations and all, math is not fun. But like if you apply it, if you relate things to it, then that's fun to do math.
Right, right. So, all right, great, great. Anyone else?
Adding anything you do, so adding quantity to anything you do in your life, adding a quantity.
Okay, so it seems to me it's similar to the second answer that I got, which was it's a way of quantifying the world, or quantifying anything that you do. Right. Okay. So I'll just add a
Right.
2 here because yeah. Yes, Ibrahim, do you want to say something? Your hand is raised. Your mic is muted though, so I can't hear you. Whoever
Sorry, that
is
was
raising.
before I already talked.
Sorry, I missed your answer.
That was before I already answered. Told my answer.
Okay. So 4 participants have raised their hands. Please feel free to go ahead. Any one of you, just unmute yourself and go ahead.
Sir, I would like to add to my previous answer. I would
Which
like
was?
to add a way of quantifying the world, but it's a little different in the sense that I want to relate it to physics, because maths is a very essential part of physics, and it helps us understand the phenomena that govern our universe.
Right, right.
Yeah.
Cool. Understanding the phenomena that govern our world. Okay, great. Well, there were more hands raised. Anyone else wants to give a different perspective?
I disagree that math should be applied only, because many ways of investigating math hasn't been based in the physical world, and their applications haven't been known until much later. That's the case for complex numbers. Before, it's thought like there would be no real applications for something that's, like but then there were applications in physics. And relating math to the physical world is kind of somewhat troubling, because you're not sure if it's actually true in the physical world. You're not sure of the link between it based in logic and the world.
Okay, link between logic and the external world. So this is a great discussion that has already started, and I'm going to put a little bit of a break in this conversation, because this conversation is, again, really great to have. But if anybody has a different perspective that they want to add, I would be really happy to have it. Yes, whoever raised their hand with it.
Sir, I'd like to add to my answer that math recognizes patterns in the world, might be in the universe, and those patterns or similarities between things act as principles.
Okay.
So first we have like basic principles that act as the foundation of maths. And I also that maths actually provide the foundation for other sciences.
Okay, so foundation, you said something about foundation of mathematics, which comes from the principles, and then itself is a foundation for other sciences, right?
Yes.
Okay, great. For other sciences. So by other sciences, I believe you mean physics, chemistry, biology, economics, stuff like that, right?
Yes, sir.
Okay, great. Excellent answers. Anyone else still raising their hand? Let's see. I don't see anyone else raising their hand. Okay. Any more answers? No.
Can I add
All
something?
right. Yeah, sure.
Okay, so I want to say that math is something abstract which helps us to understand different concepts in our everyday lives.
Mm-hmm.
Such as, before in many years ago when math didn't exist, so there was no way to specify things. But then we
Right.
used we started using math to understand things in a way that we could communicate with each other to make use of it.
Okay, communicate and make use of it. Could you give an example?
Like in older times, there wasn't any way to write things, right? So, but then when we started using math and we developed numbers and the basic operations, so that was based on the principle of what we saw in everyday life. If we multiplied things and then if we added things, for example, so we could use that to in our everyday use.
Right. Okay. Great. Adding and multiplying things. That's great. All right. Yeah. Anything else you want to add to that?
Yeah, I would like to add something. Extending to what the previous student has said. When we talk about math is something which is uniform throughout the world or the universe. Like you could have arguments about everything. You could have arguments about every other subject except math, because math is like fact.
It is fact. Okay. All right. Anyone else?
One of the philosophical questions behind math is whether it's invented or discovered.
Yeah. Yep, that's a very important question. So here's an interesting question: is do we discover mathematics or do we invent it? That's actually a great question, and I think it's sort of similar to the kind of debate that you have between doing math for the sake of doing math and applying it to the real world, and so it's whether it's discovered or invented is really a question of, was there something external out there that our mind is connecting to and just discovering it and figuring it out, or is it just a construct that we're inventing in the world? And there's lots of interesting things to talk about, especially the fact that it's turned out to be so useful, and it's at the absolute centerpiece of every advancement that we've made as a species, perhaps, right? So it's turned out to be really useful, regardless of what people, how does mathematics makes them feel, and how do they feel about whether we should be doing it just for the sake of doing it, or should we be applying it to the real world. It's one thing that everything that everyone can agree on is that it's turned out to be extremely, extremely useful, right? Okay, so this was a great answer. I would
like to add.
Yeah.
Hello?
Please go
ahead. I would like to add to that question. Not just a discovery or invention, or was it a realization? Because did math already exist, but we didn't realize it? We just used it normally without realizing.
So I would sort of lump that together. I'm not sure if you mean, so I would lump that together with discovering, because I think you're still getting at the idea about there being something in the world and then us discovering it. But perhaps the subtle part where you're where your answer might be slightly different is I suppose you're trying to get at that it was already in our minds and we were realizing it. Is that what you're getting at?
Yeah, we just used it. Was there, but we just used it without actually knowing.
Okay. Interesting. Yeah. So it's a great question, and I actually don't want to get into that debate because it's a long debate. But I would like to actually highlight a few things that I really liked about the answers. And actually, they were all great answers. But something that we will be building upon is it's definitely a study of objects, of abstract objects. And even let me just extend that idea and lump it together with the patterns, right? This pattern thing and the studying of objects thing. And I would actually, the word that I actually really like is that it's a study of perhaps of structures. When you identify principles or similarities or generalizations, you actually end up discovering a whole structure in mathematics, right? That word is really appeals to me as far as what mathematics is about. But of course, that's not the only thing that we do. Another thing that jumped out to me in your answers was this particular thing that it's a form of science which is built upon axioms and logical principles. So again, that sort of idea about it being every field of mathematics sort of being a structural thing where you start off from a few simple rules and then you build up on them and you try to see where it takes you. That sort of pattern is visible in almost every sort of field that you go into, whether it's the number theory, whether you go into, you spent a week doing geometry and you started off, Dr. Danish was frequently going back and forth with this idea of, building blocks. You build something from basic structures and you have some operations that you do on those building blocks and you see what new objects you get and what patterns you end up getting. And certainly what's important is that, it's turned out to be very useful. So you quantify the world through it, we make sense of our world through it, we attach numbers to it. It almost makes it, makes things a bit more objective, I believe, when you put some quantification on it, even though that's interesting question about what things you can quantify and what things you can't quantify. And actually that's a nice point to bring you to the other question that I wanted to ask today. And again, it's sort of a philosophical question, but I'm quite interested in given the responses to the first question, I'm actually really interested in what kind of responses I get to this one, which is how much mathematics do you know? So now I've almost asked an answer that seeks to quantify something that perhaps is quite difficult to quantify, but I'm interested in seeing how you would quantify it. Anyone willing to make an attempt at answering this question?
So I would say one word that's limited, that we do not know an infinite amount of maths, and it's that we know a finite amount. We know a limited amount of maths.
We do not know an infinite amount, only finite. That's interesting. Okay. Anyone else?
Can I have a go?
Yeah.
So I think that this question is very hard to answer because we don't know the end of math, right? So we can't compare how much we know because we don't know how much of math exists. So if you were to ask me how much I know, it would be very a very small amount because there's a lot of math which is still to be discovered.
A very small amount. Okay. And a lot of mathematics yet to be discovered. All right. Anyone else?
Sir, we can take the traditional route.
Like
we can say we know a fixed curriculum, like in math, we have a certain syllabus and that many topics.
Okay, and so number of topics, maybe. Okay.
Yeah, or we can go the, I would say the other route, which I would think is the philosophical route, is that because maths, as even when we know topics, and we can apply topics to other things and then find principles in other things, because we don't actually know about like enough about the universe. So maybe other things to discover and other topics to discover, like the same thing about what the second point was, that we do not know how much that exists.
Okay.
Yes, sir. All right. That's the one.
All right. Anyone else? Great.
Yeah, I'd like to give it a go. So we've existed, like the humans have existed for like 200,000 years. Okay. And it's just that we know this little math, जो कि हमारे computers, libraries, search engines पे fit आ गई है. ठीक है. And we honestly have not cracked the code to the universe. We have not cracked anything beyond the observable universe. So we technically don't really know anything yet.
Okay. So let's say only know what we have in libraries and computers, but we don't really know anything. But we don't know anything really. Okay. Anyone else?
Sir?
Mm-hmm.
Sir, I would like to add that perhaps as a person, I merely cracked the surface of maths, but where it could take me, I think no one can say for any discipline that they can, master the whole sphere of that discipline. And especially for sciences, I think the space with which the discipline evolves, it's so rapid that when you know one principle, there are 10 more to understand and to figure out. So I don't think there is a possibility of ever trying to completely grasp maths with just one person.
Right, but that wasn't my question. My question was simply, how much do you currently know?
Yeah, for that, I think I barely scratched the surface.
All right, barely scratched the surface. Okay. That feels about right. Yeah.
Is there a limit to knowing? Because each day you learn something new in mathematics.
I don't know if there's a limit. Yeah. I do know there's a limit to how much time I would be alive to actually think about it. So there's a limit right there.
But on the topics of mathematics, there's no such limit.
There's no such limit. And
yeah,
I would actually like to argue, this may seem very trivial to all of you when I make that argument, but I would like to think, sure, we do not know. I do agree with the first part of the first answer, which is that we do not know an infinite amount. I think that's correct. But I would like to add to that, perhaps it's a way of making myself feel better about it, that I don't really agree with the second part of your answer, which is that we know only a finite amount. I think each of us, even at this level, I can make a case that we already know an infinite amount of mathematics, right?
Yes, I agree with that.
You agree with that, and could you make that argument for me? How would you make that argument?
Because we already know. Just like
just
like someone said, we may have to us we perceive we understand it, that we scratch the surface. But when we go into it deeper and deeper, we know a lot more than we think.
I don't even want to make that philosophical argument. I actually want to make that argument a bit more concrete. I want to give you an argument that maybe convinces you that we already know an infinite amount of mathematics.
Can I try?
Yeah.
So I think that you would make a case, like the topic of numbers. We can say there's an infinite amount of numbers.
Yeah.
So that's why, or that's like the amount of knowledge there is infinite.
Right.
I think that case would be solid. But sir, the finite thing would be that there's still numbers.
Right.
That the topic is numbers, right? And we can derive irrational numbers, rational numbers, natural or integers, or we can derive from that. But all of it are still limited to what it is. They're always going to be numbers.
Right. That's perfectly. Those are two perfectly valid ways of looking at it. Here's one way of making that case, which you almost made it for me, but I would like to make it that we already know. And instead of making infinite amount of numbers, I want to say I already know an infinite amount of mathematical facts. And the way I know an infinite amount of mathematical facts is as follows. Let me just say, I know that 2 is greater than 1. I also know that 3 is greater than 2. I also know that 4 is greater than 3. I also know that 5 is greater than 4. Very trivial, but you can keep going on, and you know that this is, you can do it for any number that you have the time to look for. 101 is greater than 100. And again, what I denote by these dots is that there's an infinite amount of these mathematical facts, and you all know these facts. Nobody needs to teach you these. And from that simple argument, and I would like to say that's not even the only case in which I know infinite. I can actually say 3 is greater than 2, and it's also greater than 1, which is greater than 4. So there's actually, within this one particular fact, is hidden a couple of more facts, which is that 4 is greater than 2, 4 is also greater than 1, and 4 is also greater than 0. And so within that fact, you also have an infinite number of facts that you can think of it. And that's just one comparison operator that I've put in there, which is greater than. And you can turn it around, and you can turn it around for negative numbers perhaps, and so on. So from one perspective, you know an infinite amount of mathematical facts. On the other hand, we also, like I think you tried to make the point earlier, all of this can be made really compact. All of these infinite number of facts can be put down into one simple argument, which is I can write it mathematically, and the language of mathematics and the symbols that we've come up with allow me to write these facts in a much more compact way. Every time I want to state something like this, I'm not going to write an infinite number. I don't have, firstly, infinite amount of paper to write all of them. I don't have an infinite amount of time to write all of them. But I can capture the essence into something simple. For every n belonging to n, n plus 1 is greater than n. And that's a simple mathematical statement. Does everybody know these symbols that I'm using? So this is this one.
Yes, sir.
Yes.
Great. Let me just, so this means for all, and this just means belongs to. Right. So all I've done in this one little box here is that I've just said that I know an infinite amount of mathematics, and now I've made it succinct into just one fact, right? And now all of my, it sort of feels like I've condensed my infinite knowledge in a statement. It's an interesting thing that mathematics allows you to do, and I would like to state that it's really efficient. Whatever this language is, it's quite efficient. But before we move on, let me ask you another question. You all understand, does anybody have a problem with the statement that I've just written?
No, sir.
No, so let me ask you, what is the symbol that I've just written there?
The set of natural numbers.
Okay, so familiar with it, it's the set of natural numbers. What is the set of natural numbers?
One is in the natural numbers.
Okay.
For any x in the natural numbers, x plus 1 is also in the natural numbers. There is no natural number such that the x plus 1 equals 1.
There is no, could you state that again? There is no
natural number.
Okay, such that, let's say there is no natural number such that?
One more than that number equals 1.
Right, so x plus 1 equals x. So let's write it something like this for all x.
No, I meant 1 has no successor in the natural numbers.
Okay, so let's say 1 has no successor?
No, 1 is the successor to no other natural number.
Okay, 1 is the successor. So did you mean x plus 1 equals to 1?
Yeah.
Okay, 1 is the successor to no natural number. Okay. So how about I write it like this? For every x, how would I write it? So there does not exist an x such that x plus 1 equals 1. Are you okay with that statement? Does it capture what you were trying to say?
Yes.
Okay. All right. So taken together, all of these facts sort of give me the natural numbers, but I still have a question. What is this plus sign? How do you define this addition operation?
So adding
something into another.
What do you mean by that? What does adding mean?
Addition by 1 means the successor of that number.
So addition by 1 means the successor of that number. So of that number. Now, this is all great, except that I don't know what you mean when you say successor.
Are you asking the question as if there is no maths, meaning you don't know? I have to explain to a person who does not know an ounce of maths, so I have to explain this to him.
So what I'm doing right now is I'm basically, it sort of feeds into the second answer that I got, which is that it's built upon axioms and logical principles, which is that I want whatever we are talking about to be as precise as possible. So I want to really know when we write these symbols, what do we really mean? When you say addition, sure, we've sort of been taught that 2 plus 1 is equal to 3 and 3 plus 2 equals to 5. But what is, like, these are facts that we know, or how do you really define it? So I am really interested in the definitions, in the precise definitions of these terms. So when you tell me that there's a set of natural numbers, I want to know what you mean. When you say addition or when you say successor, I don't know what you're talking about. I want you to help me make it as precise as possible.
The successor of a number can be defined as anything. So we start off defining a 1, then we can just choose any other symbol to define what comes after that, and then what comes after that. If we're going for a base 10 system, we'll probably only define like 10 and then just use that 10 symbols. If we're going for like a unary system, we just keep adding more and more symbols.
Right. So at this point, it seems like you've accepted that the symbols that we use are sort of arbitrary. So if you're working, you said if you're working in the decimal system, then it's a base 10 system. Then you have 10 symbols, and then you sort of go through them and define. So one way of doing that is we have this. The successor of 1 is, let's say, 2, and the successor of 2 is, let's say, 3, and the successor of 3 is, let's say, 4, right? But is there anything special about this symbol? Is there anything special about this symbol or this symbol that's part of the definition of natural numbers?
They describe. Each of them describe a specific quantity of whole objects or whatever that thing or things may be.
So if I were to change this and say
so one would define
the successor of 1 is 3, and the successor of 3 is 2, and the successor of 2 is 4, am I doing anything wrong here?
Now, sir, it would actually, I think that no, because in a other universe, in an alternate reality, for example, the definition of 3 would be describing actual like 3 objects would instead of 3 objects there would be 2, but we call it like in other alternate reality some sorts, 3 would be actually describing 2 objects,
right,
and 2 describing 3 objects. That's what
right.
I would
so
think.
at this point, and do you agree with that answer, Ryan, or do you have something else to add in that answer?
Yeah, I just have something to add. Right now, I can't say that these are whole numbers because there's no such thing as a fraction yet, because without the natural numbers, there's no rational numbers. So there's nothing to compare it to. So I can't, right now, I can't describe what 2, 3, 4 actually mean, because then I would be trying to prove an axiom, and you need foundational knowledge. All I can do is kind of intuitively show you that this is kind of what I mean.
Right, that's absolutely right. I don't really, so there seems to be a sort of intermashing of what we've been taught and what we use, and what we're trying to do here at this point is we're trying to clear off the dust, right? And the dust that we want to clear off is the language that we use in our daily life and the symbols that we use. And at the real core of that, so what I see now is that there are some symbols that don't really matter. If I were to change these symbols, right, and if I were to use another language, right, and if I were to do that, it doesn't seem like it changes anything, right? These are just symbols that I'm using. But there is, at the core of these, regardless of what symbols I choose, there seems to be a mathematical idea right here. And I want to clear off the dust as much as possible. So if I do accept your definition about that, when you say you're adding something, adding by 1 means the successor of that number, I have 2 questions. The first question is, well, what is 1? And the other question that I have, can I add by any other number? That's add by something else. And the question that I still don't feel satisfied about, which is, what is this? What is a successor? If it can be, when you say it can be defined as anything, I'm not sure what you mean.
You can add by any other natural number by adding by 1 multiple times, but now I have to add what adding by 1 means.
Right.
Which is difficult.
Right. Okay. So yeah, and it seems that the question really is at this point, is there a systematic way where we can start off from something really, really basic? Now, it seems that we're sort of stuck at this point about just accepting one for what it is, and we just assume that everybody understands what we mean when I say one. And if that's possible, then maybe I don't need to define what is one. And if everybody understands what I mean when I say successor, that's perhaps the best I can do at this point. So, but I'm still not satisfied, and I'm just wondering if there's a more, there's a cleaner way, and there's more dust that we can clear off, right? So we've sort of cleared off the dust of the symbols. We've sort of cleared off the dust of, thinking about these other symbols. And actually, you know what? I can just get rid of, I just need one symbol. I need just this symbol. And the other symbols don't matter because I need one more symbol, I guess, which is this addition sign, right? And from this, can you tell me how to just write down the rest of the objects that I have in mind?
One add one, one add one, what add one.
Yeah, I was thinking the same thing.
Right. So I don't need those symbols really. But again, the point is, I can only do this for so long. I can't really enumerate all of these items, right? Well, because there's an infinite number of them and I don't have infinite amount of time. So we sort of leave it as a dot, dot, dot. But again, even in this, some precision is lost because I'm assuming that everyone who sees this definition understands what I mean by dot, dot, dot without me having to explain what this dot, dot, dot means. So it's sort of, if I define the set of natural numbers, if I end up with this definition, it's still a question of everybody needs to understand what I mean by one, everybody needs to understand what I mean by plus, and everybody needs to understand what I'm doing over here. What are these dot, dot, dot mean? So, but I'm hoping everybody, at least in this audience, understands. So I'm able to communicate that idea, right? And so you can notice that if you want to get to the foundational ideas, and many rigorous attempts have been made, and some, of course, we do have successful attempts at defining the set of natural numbers, and I think the most comprehensive attempt at making the whole enterprise of mathematics rigorous was done by Russell and his colleague in the Principia Mathematica, which is basically trying to find the foundations of mathematics. And the foundations of mathematics that they tried to set down were set down in set theory, right? And I invite everyone, if you're interested in really how natural numbers can be constructed through set theory, that would be a really useful exercise. We don't really have the time to go through those rigorous steps because it takes some time to get to the basic ideas and then start building up what we really need. And so even just to build up this idea of a one and of this plus and of these ideas, it takes some time. So not only is the language of mathematics efficient, but you also need to be really precise, right? You need to be really, really precise. And when you're defining something, is that there should be no ambiguity in what you're defining. So in the set of natural numbers that I've written, that I've defined so far, there is still some ambiguity that I sort of have to live with, hoping that everybody understands what I'm talking about. And that's just the set of natural numbers. Yes, Saad, you have a comment?
Sir, what you said about ambiguity, I would like to add that even if we define one, everyone, because we're human, we do have this subjective, we can have subjective, we can have different perspectives. So there's always going to be an ambiguity. Everyone's going to, fail, or they will like to argue like why this one is the way it is.
Right.
Right.
But can you really, I mean, I haven't encountered anyone yet, and I don't expect to encounter anyone. But if I were to ask you, do you understand what I mean when I talk about the number one? Would you say that it's subjective, or do you think there's a chance that the idea that I have in my mind about the number one is the same idea that you have, or do you think that there might be some difference?
Well, sir, now I don't have any difference. I know that one refers to what it does is one object, one quantity of anything or something. But however, it could have been another way, that maybe like if we swap, like what you said about swapping 2 and 1, or the symbols, right?
Right.
So the definition of 1 could have been given to 2 instead of just one object. We could have said there are 2 objects, but
right. But
reality,
I'm not talking about the symbol. There's a symbol that I'm referring to, which is this. But I'm not asking you about that symbol. I'm asking you about the idea of one, which the symbol could be anything. The symbol could be 1 or uno or 1 or ek, or anything. But I'm really talking about, and I hope that you understand what I mean about when I say I'm talking about the idea of number one, right? And maybe just one object right there. So do you think that
that's where I'm having difficulty? Because I deeply, I kind of understand it, but then again, I have no words to put it in.
But do you think that because the idea is shared between us, or do you think there might be a chance that our ideas might be different?
I think that our ideas are shared because many different cultures have grown apart but have invented one by themselves, have thought of the idea. And that's the best you can do. You can't prove that something like this exists. If I have a statement P, I have to prove it, and then I have to go to P2, then P3, then P4. Either there's an infinite regress, which can never, or there's a base idea, and that basic idea has to be an axiom, like the existence of one.
Right. So there's an infinite regress, that to avoid that infinite regress, we have to settle on some axioms, right? And the question really is, what are these axioms that we're willing to settle down on? It seems like the best that we could do today was that settling down on these axioms, that there's an entity that we represent by this number, this symbol that we've actually come up with, and we all agree with these axioms. So it's really a question of what axioms are you willing to settle on to avoid this infinite regress, because whatever you define, so when you defined addition, you defined adding by 1, and then we ended up on the successor. But if you define the successor, then again, you have to define it using something else, and that needs, again, a definition. So there's an infinite regress, definitely, you're absolutely right. And to avoid that, we need some axioms. So the question is, which axioms are we willing to settle down on? Okay, great. And so you can see that this definition that we've come up with, just for the natural numbers, we can perhaps now extend it if we're willing to give this number the symbol of 1 and represent this as this symbol and represent this object using this symbol and using this object as this symbol and this object as this symbol and so on. And if assuming, I'm not going to do it, but assuming that everybody understands that how I've defined these numbers, then maybe I can define this as 1, 2, 3, and so on, okay? And so perhaps I do have the set of natural numbers, even though it didn't seem very satisfactory. But now you can imagine the kind of difficulty that we might face in defining the set of perhaps the integers, the set of rationals, the set of reals. So let's not get too rigorous because we've already done one exercise of making things rigorous and we know how it goes. So let's just talk about these sets. What do the set of integers have?
Negative number and 0.
Right. So we have this new entity, 0, and then we have the same entities as before, but also now we have their negative counterparts, positive, negative, positive, negative, positive, negative, right? What about the rationals?
Fractions of the integers, ratios.
Right, so ratios. So perhaps these are the set of numbers, let's say R, such that R is P over Q, where P and Q belong to the set of integers. Is that a satisfactory definition?
And Q is not 0.
And Q is not 0. What happens when Q is 0?
Undefined, sir.
It's an undefined quantity, and P over 0 is an undefined. Don't have a definition for it. How do you feel about me making the claim that P over 0, just written a statement, there's a few mathematical symbols involved, and let me say that P is an integer. How do you feel about this statement?
Bad.
Bad?
It can also be negative infinity.
So the P over 0 equals infinity. If I were to put it in actual words, like something divided by nothing, it would be something. How would it be infinite?
Right.
Because it's being divided by nothing there to begin with. If there's nothing there, it isn't being divided. So it stays the same.
But do you have any problem with this symbol, though? I've written this symbol. What does it even mean?
Well, it depends on what you ascribe it to.
Okay, and what do we naturally ascribe it to?
So the mathematical facts that we discussed, that we know infinite amount of mathematical facts.
Right. No, I'm really getting at, I'm just asking, I've written a symbol. Nobody has an issue with the symbol that I've written. But again, you do?
Yeah. Well,
what's your problem with it?
Since division is the opposite of multiplication, P times 0 times any number is 0. So then any number divided by 0 could be 0 divided. Any number divided by 0 could be any other number, not just, or is that only for, sorry, Oh, right, right. So if you divided 0 from both sides, assuming that worked, you could say P 0 of 0 is any number.
Uh-huh.
So it doesn't have a fixed value.
Okay, but before we even get to that, I should just ask, what is division?
Is the inverse of multiplication.
Okay, so you want to define it as the inverse of multiplication. What does that really mean?
Making parts of a whole of something, making parts of one whole.
Making parts of a whole. What is inverse of multiplication? Ryan, could you make this idea more precise about inverse of multiplication?
If P times Q equals R.
If P times Q equals R.
Then R over Q is P.
Then R over Q is equals to P. Question, what is times?
P added to itself Q times.
Right, so P times Q is P plus P plus P, and this is done Q times.
Or Q added to itself P times.
Or Q added to itself P times. Okay, things would, what if I said that this is pi?
We're still in the rational, so.
Okay. All right. So we're still in the rational. So Q is an integer. So P and Q are integers?
Yes.
Okay. All right. So we can do an integer number of additions. So that's fine. So it seems like I have now gotten down to the things that I had settled down on, which is addition, I understand. And adding things Q times, I also understand. And these symbols, I understand. So this definition I'm happy with, well, for now. And this definition then makes sense. If P times Q equals to R, then R over Q is equals to P. Okay. And so now tell me what happens. What was the issue that you were getting at when Q equals 0?
You're adding something to itself 0 times.
Right. So when you're adding something to itself 0 times, you're not really adding anything. So then you have 0. And so then it's sort of, you have to specify here that Q shouldn't be 0. Because if Q is 0, then you have this weird idea, if we follow this definition, that 0 over 0 is P, which is a weird idea. Okay, so we've sort of removed this possibility from our definition by just specifying that Q is not 0. Okay, and so perhaps we do have an understanding of the rationals now. And so you can see how this complexity sort of starts getting higher and higher. And let me just mention the set of real numbers. What do you understand by the set of real numbers?
It includes irrationals.
Okay, so it includes irrationals. What else does it include?
Every
numbers.
Sorry?
It includes Q.
Okay, so let me say it includes Q and irrationals. I have a question though. What are the irrationals? We haven't defined them yet.
Those numbers which cannot be in the form of P over Q.
Okay, so irrationals are numbers that cannot be written as P over Q. And what are these numbers then precisely?
I.
Oh,
Pi.
square root, for example.
Pi, okay.
E.
Okay.
Square root of 2.
Okay. So this number I don't know, this number I don't know. And when I say I don't know, I of course mean based on the things that we've defined so far. I don't know what's pi, I don't know what's c. This, on the other hand, is something we can get into. What is the square root? So I know this number that you've written here because we said, you know, we can define 1 plus 1, and I'm going to call it in a shorthand way using the symbol of 2, right? I'm calling it 2, but I don't know this symbol yet. What is this symbol? What does it signify?
The inverse of squaring.
So the inverse of squaring, right?
Multiplying
So
by
it's a
itself.
really, so multiplying by itself is what?
Squaring.
So squaring, we understand that it's a multiplication with itself. Multiplication.
The square root is a power of half.
So, okay, I'd say power of half. Okay, so based on what we've been doing so far, which of these definitions do you think I would prefer? Would I say it's a multiplication with itself, or would you think I prefer a power of half?
Multiplication with itself.
Why?
Because we haven't
we've been
defined
doing
our exponentiation yet.
So I've already defined what multiplication is so far. Here, Ibrahim helped me do that. So what does power mean?
But yeah, we haven't defined power, so that's why I was saying.
What's a power? And then what? Well, a half is something I understand now because we've settled on the definition for rationals. So there is a number that's defined as half that belongs to the set of rational numbers. So what is the power really?
Multiple multiplication with yourself, with itself.
Multiple multiplication with itself. So could you give me an example?
P squared is P times P.
Okay, P squared is P times P. What is P cubed?
P times
P times P.
Okay, I understand all of this now. Perfect. I feel like I have a grasp for what power is. P times P to the 10 would be P times P times P times P times P. And I do this 10 times. But now, what does it mean to write P to the, how do I multiply P with itself a half time? Do I just write this or something?
1 over P.
So if you say that this is under root P, when I ask the definition of a square root, and you say that it's the power of half, and then I ask what is the power of half, you tell me that it's under root P, you're doing the circular definition.
Well, P over half is the number which when squared equals to P.
Okay, so P over half is the number that when squared gives P. Okay, I could live with that, except I want to know, does this number always exist for every other number? Is there such a number?
Well, there's
If
two.
P was 2, then is 2 raised to the half really a number?
It's an irrational number. What it be?
Okay, so we're settling down on this idea of it being an irrational number, but so you see what the friction is at this point, because I started off by asking what's an irrational, and you gave me a couple of examples, and which was one of them, which was square root of 2. And now I'm asking, does the square root of 2 exist? And you're telling me that it's an irrational number.
One
So
minute.
what really is it?
Before we do that, I think we need to justify why there's a half exponentiation, not anything else.
Okay. So let's get rid of this business of a half, and let's just settle on this symbol, right? Let's not read too much into this half. Let's say this is a number that when squared gives p, so that I get rid of this issue with the half. Okay, so it's just a symbol. How can I make it more precise?
We don't know yet that square root of 2 exists.
Right. So the question really is, does this make sense to write a number as square root of 2? Is it a number really in the sense that we understand numbers?
Yeah, since we only know rationals, we have to prove or disprove that square root of 2 can be written as the ratio of 2 integers.
Okay, so, but then the question really, before I even answer the question of how it can be written, right? Can it be written as a ratio of 2 numbers? I'm getting at a more, I don't know, an existential question, which is, does it even exist as far as numbers are concerned? What gives me a justification for thinking that there should be a number that when you square it gives me 2? Why do you think that such a number would exist? Why can't we just say maybe there is no such number and leave it at that?
Can I give this a go?
Sure.
So when we talked about natural numbers right in the beginning, remember how we talked about having 1 and then we could add 1 to it, and then we could have 1 to it, add 1 to it. Mm-hmm. So it's somewhat like that only. We could look at it in a general perspective, that it's a pattern which sort of exists in all the other numbers, so it also must be existing in 2. And secondly, when we talk about precision or existence is basically a mere question of precision. So when we say that the radius of a circle is let's say 4 centimeters, but it's actually, if we get even the most precise machines, we cannot make a proper circle with a radius of 4. So similarly, if we look at it in the precise lens, we cannot really get a perfect square root of 2, but I'm sure it does exist somewhere out there.
Right. So I'm really getting at this. Yeah. Anyone else?
The reason why square root of 2 should exist is because there's a triangle that it has a right angle triangle that has a hypotenuse of 2.
Right. So
yeah.
Okay, great. This is and what are the lengths of the sides of the side angle triangle?
Square root of 2.
No, I'm talking about the width and the height.
Oh, okay.
1.
The 1, right? So if I take a right angle triangle with length 1 and height 1, and now if I connect these two, the question is, if you accept this theorem, which everybody knows, I expect everybody knows, which is the Pythagorean theorem, that if you have any right angle triangle, and if this is, let's call it the length, and let's call it the height, or let's call it the width and the length, so let's call that the hypotenuse, or maybe just A, B, C, then we all know that A squared plus B squared is equals to C squared. And now by that very simple construction of us thinking that there must be a triangle of length 1, height 1, and you can put them at right angle triangles, and we can connect these lines together. And if we apply Pythagoras theorem, 1 squared plus 1 squared equals to c squared. And so it gives me that 2 equals c squared. And now I've reached this same definition, which is that there is a number that when squared gives us 2. So if there's any such number, that's the length of this really simple triangle that I've drawn. And so when you feel that feeling in your head that, you know, square root of 2 should be a number, maybe that's one of the justifications for it, which is, I don't see why making such a triangle should not be possible, because if square root of 2 isn't a number, then you can't make such triangles. But clearly, I don't see anything that stops me from making this triangle. And so it sort of compels me to look further into the idea that there might be, and so now I can just, you know, shift the symbol. I don't want to have a square here, so I define it as an inverse, that I'm looking for a number such that I define it as square root of 2, because I want it to have the property square root of 2 that when I square it, and by that only I mean square root of 2 times square root of 2, it gives me 2. Right now, I'm not talking about any powers or multiple. I'm not saying that these cancel out. No, I'm not saying that. All I'm saying is that I feel compelled to believe that there might be a number which, when I multiply these two together, it should give me 2. And that number is the number that gives me the length of this hypotenuse of this triangle. Okay, so we've sort of run out of time, and I don't want to extend this session any further. So let me make a few concluding remarks, which is that what I wanted to impress upon you in this session is that we need to be as precise as possible, and we need to dust off all of the dirt and get to the basic ideas and get to the really core structures that underline these structures that we've taken for granted, really. And most of your studying so far, for a majority of you, you've learned these things as pure fact. And one of the things that you start changing as you transition from high school mathematics to undergraduate mathematics is that you stop taking things for granted and start questioning and looking more deeper into the something. Is my screen still visible?
It's black now.
No,
Okay.
sir, it's black.
Something happened to my screen share. Okay, we're back. So yeah, we need to, as you transition from high school mathematics to undergraduate mathematics, you need to start getting more comfortable with the rigorous nature of how you do mathematics. So there will be a lot of symbolism that will come into play, a lot of formalism that will come into play, and a lot of really trivial things that you'll have to prove. But you have to understand that all of this is done is because you want to know what are the axioms that you have to settle down upon, right? You have to get to the core central ideas. Even what we've done so far is, from a rigorous mathematical point of view, very sort of naive, you would say, and you will, as you start reading more advanced mathematical books and proofs, you'll start getting into deeper and deeper ideas, and which may look a bit unfamiliar, but the point is that you want to construct, so you want to construct perhaps a set of natural numbers, or an even more difficult exercise is to construct the set of real numbers. And what you really want to do is, when you define them, you want to capture the essence of what you already understand about them. So when I go ahead and define the set of natural numbers, I want that definition to encapsulate everything that I already know, which is 1 plus 1 equals 2. 5 plus 1 equals to 6. And I want to capture those ideas, but I also want to capture the idea that is 2 plus 1 equals to 3, but also 1 plus 2 is also 3, which is this idea of commutativity, and you discussed other ideas about associativity, distributivity, and so on. So you want to be as precise as possible. And we will look into the square root of 2, we'll look into the irrationals, and we'll, in the next class, we'll look into a bit more about proofs and, you know, making logical arguments, making mathematical arguments, and really trying to find the holes within these mathematical arguments. So I think that's it for today, and I don't want to extend this any further. Do you have any questions or comments in what we discussed so far? And let me just see what we have in the chat. Whether it is, so, okay, I think it's how we give meanings behind every science, okay, to solve real life problems, it's independent of the physical world. Yeah, I think one thing that I didn't touch upon in a bit more detail, and I think it's a longer conversation about whether mathematics is discovered or applied, or this idea of somebody said what it should be, and it's a really interesting question. I think we will have a longer discussion on this on Discord. Anything else you would want to add? Anyone?
Sir, will you share the document you've written in front of us?
Sorry?
Will you share the document that you've written in front of us?
Yeah, I'll share everything. I'll share these as a resource.
Okay, thank you.
No worries. Okay,